Hi guys, welcome to the Matter Part 2 tutorial. In this tutorial, we're going to talk about a theory known as the kinetic molecular theory. And let's break that down word by word. Kinetic, remember, refers to motion. Molecular refers to molecules, which are small pieces of matter. And a theory is an explanation of observations. So, translated into plain old English, kinetic molecular theory becomes moving particle explanation. It's the moving particles explanation. Explanation for what? Well, it's an explanation for why matter behaves the way that it does, mostly when we heat it. So here's the deal. We believe, scientists, that all matter is made of particles. We don't have any direct evidence of this. We have a lot of indirect evidence, similar to the kind of evidence that we collected with our black box lab. But we're pretty sure matter's made of particles. You can call them atoms, you can call them molecules, or you can just call them particles right now until you know the difference. The particles are in constant motion. Even the particles in a solid are moving, and that's kind of hard to get students to wrap their heads around because solids just don't look like they're moving. They're not moving around relative to you, but if you could shrink down to the size of the particles and look at the particles themselves, in a solid, they would appear to be vibrating in place. You can't see this vibration at the size that you are. It's like trying to see something that's a million miles away vibrating in place. You just can't. But that motion is there. We believe that that motion was given to every particle in the universe back during the Big Bang, and every particle's been sort of moving around ever since. We also know that we can increase the motion of particles by increasing heat energy. In fact, heat technically only exists if you have particles of matter around. You can't have heat without particles, which is why outer space is so incredibly cold, because there's very few particles floating around in space. However, when you do have particles, their motion, how quickly they're moving, is heat. The speed of the particles is the heat. So heat energy and motion of particles go together. And then finally, as the particles speed up, they have this tendency to spread apart. And that's because they start colliding with each other and with the walls of their container. And so the more force they have to collide with each other with, the further apart they rebound. And I have to add one more thing to this list. Okay, so I put this one in red because it's the hardest one to understand. Here's the deal. There's lots of different types of matter. You can think of it this way. There's lots of different types of atoms. If you've ever seen the periodic table of the elements, and I have a copy hanging on the hood in the back of the classroom, you know that there's hundreds of different atom types. Each one of those different atom types has a different amount of interparticle attraction. You kind of have to think of atoms and particles as being like tiny magnets that are attracted to themselves. They pull together naturally. But different types of matter have different amounts of attraction. It's like they're different quality magnets. Some are really strong magnets, some are really weak magnets. And this is what makes the difference between the different types of matter that you see. So for example, generally speaking, most students are aware of 3 different types or forms that matter can be found in. We refer to these as states, or there's another word, phases. There are actually 5 states or phases of matter, but for right now, let's just focus on the 3 we're familiar with. You've got solids, liquids, and gases. So particles that make up matter can be a solid, a liquid, or a gas, and that really depends on how far apart the particles are and how much motion they have. Solid particles vibrate in place, and we can show that by putting little hash marks like this that show the vibration of those individual molecules. Liquid particles have what we call rotational motion, and we show that with these little curved arrows here and there, showing that the liquid molecules are able to rotate. They can slide past each other, they can roll around each other, but because they're attracted to each other, they can't get pretty far apart. They're sort of stuck in a certain range around each other. It's like they can get within a certain radius of the neighboring particle, but they can't totally escape. But they can roll around. So liquids have that ability to flow. Gases are particles that are completely broken apart from each other. The attraction is completely overcome with speedy, speedy motion. So the particles are jetting off in straight lines in any direction they can go in. So look down at the bottom at the descriptions of solids, liquids, and gases. You need to be able to draw a picture of a solid with these motion lines, and you need to be able to tell me that particles in a solid are, generally speaking, close to each other and rigidly bonded to one another. They're stuck in place, and because of that, that means that a solid will hold its shape, it has a definite shape, and it will maintain its volume. The amount of space it takes up will stay the same. Liquids, on the other hand, the particles are still pretty close together. They're still packed together, but they're able to flow. They have that rotational motion. And because of this, their shape can change if you change containers. You can pour a liquid from one container to another, and the shape will totally change. However, the amount of space the liquid takes up is still determined and fixed. It's still definite. You can't pour it from one container to another and have suddenly more liquid. On the other hand, gas particles are really far apart. In fact, if you've ever thought that you were looking at a gas, if you thought you saw a gas, you were probably wrong, because most gases are completely invisible because the particles that make up a gas are so far apart and so tiny that you can't detect them with your eyes. It's a rare gas that reflects any light at all, and there's just a couple of them that are colored. A lot of times students think they're seeing a gas when what they're really seeing is a mist of a very fine liquid. So like when you see steam, there's liquid, there's water in the steam in the gaseous form, but you can't see those particles. They're too far apart. What you're seeing are the particles of gas that have come back together and started to form a cloud, and that's what you're looking at and thinking of as the gas, but it's not. You can't see the gas, it's invisible. Gases have an indefinite shape. They can take the shape of whatever container you put them in, and unlike liquids, they can expand outward to fill any shape, so their volume is not fixed or definite. And you probably know that you can change the state of matter by changing the temperature. If I add heat energy, if I go this way, if I add energy, I can make my particles move faster and spread further apart. If I decrease the amount of energy, I can make my particles slow down and come closer together. And they'll come closer together because they're attracted to themselves. So they have some natural attraction. Now I want you to think about whatever room you're in right now. There's probably some solids, some liquids, and some gases. Why, if everybody in the room is at the same temperature, all the different solids, liquids, and gases are all at the same temperature as you are, whatever the room temperature is, then why are they in different states? The answer is that things that are a solid at this temperature are a solid at this temperature because they are strong magnets for one another. So the heat in the room is not strong enough to make those particles do more than vibrate. Things that are a liquid at this temperature, they're fairly strongly attracted to each other, but not as much as the solids in the room. So those particles are able to slide past each other with this much heat energy, but they're not able to break apart. The gases that are in the room, like the air in front of your face, those particles have virtually no attraction for each other. At this fairly cool temperature, they're able to just totally ignore one another because they have enough energy to just spread apart. And this is why you tend to think of things like oxygen as a gas. You've probably never seen liquid oxygen or solid oxygen. But those things do exist. They just have to be, they only exist at temperatures that are way colder than you could stand to be at, so you don't tend to be around when oxygen turns to a liquid or a solid. Same thing with something like the table that you're probably sitting at, or the desk. That object is a solid, and you probably think to yourself, it can't really become a gas, but it could if you got it hot enough. It might burn before it gets a chance to melt because you're in a high oxygen environment, and so things have a tendency to burn when there's a lot of oxygen around. But if you remove the oxygen from the room and then heated it up, everything in the room would eventually melt if it got hot enough. So it's important to realize that every single substance on Earth can be in any state of matter. It just has to be at the right temperature. Let's take this information and apply it to what happened in the lab that we did in class. Even if you were absent, you should be able to follow the basic gist. So what we did in class, I introduced you to some different equipment that you could use to collect temperature, time data as we boiled water. So we put 3 milliliters of water in this test tube and we heated it, and here's our thermometer probe. And we collected data with our LabQuest, and you can see times going by on the bottom and temperatures changing on the y-axis. And what we found was that as our water boiled, we hit what's called a plateau, and that happened here at about 100 degrees Celsius. From here to here, the temperature of our water was staying the same, and that was the boiling period. Before that, our temperature was rising, and after all of our water had turned to a gas and there was nothing in the test tube anymore, after that, temperature was rising again. This is really important because temperature is actually a speed. Strange to say, but when you measure temperature, what you're measuring indirectly is how quickly the molecules of the substance are moving. So what happened is we added heat energy and our molecules sped up. And they sped up until we reached 100 degrees of heat energy. And then, for some reason, they didn't speed up anymore, even though we kept adding heat. Why is that? I'll show you. Okay, check it out. So, this is what we did. We took liquid water, right here, liquid water, and we heated it, and while we were heating it, temperature went up. That means these particles here were speeding up. An increase in speed is really an increase in kinetic energy, right? Because kinetic refers to motion. So as those molecules speed up, they're gaining kinetic energy. But then we reach this point where the molecules right here, they have enough energy now that they can do something else besides speed up. Now they can rip apart from each other to become a gas. That action of coming apart requires a lot of energy. So as those molecules change state, they take the energy we're giving them, and instead of using it to speed up, they now use it to change position. When you change position, that stores up potential energy for later. Just like if I lift something above the ground, the higher up I bring it, the more potential gravitational energy I have. Well, these molecules, as I separate them from each other, remember, they want to snap together like magnets that are attracted to each other. So the more I pull them apart, the more potential energy I store up between them because they kind of want to snap back together. So the reason for the plateau isn't that we stopped heating the substance. It's that the heat is no longer going towards making the particles move faster. It's going towards making the particles change position. Whenever a state change is happening, you will get a plateau on your heating curve. The word plateau is French, so it's spelled all funny, but it basically means flat. It's where we get the word plate from. So whenever you see a plateau on a time temperature graph, you should immediately think to yourself, why is the temperature staying the same while I'm heating it? Oh, I see. The particles must be changing position. They must be going through a state change. Okay, so the key things to remember from this tutorial, first of all, I'm not giving you a quiz on it. There's a lot of information. But the key things to remember are the 5 bullet points of the kinetic molecular theory. You will eventually need to have those memorized. And you also need to recognize the different states of matter and what makes them different from each other. And finally, you should definitely remember this, that a plateau represents a state change on one of these graphs. And I'll see you guys in class.